Welcome back, Physics 30. This is the MP1.5 blackbody radiation and Planck's quantum hypothesis. So here we'll use Wien's law to determine the peak wavelength emitted by a blackbody at a given temperature and describe Planck's quantum hypothesis. And approximately halfway in between here, I have another video I'd like to show you from someone else. Okay, so blackbody radiation, first of all. One of the observations that was unexplained at the end of the 19th century was the spectrum of light emitted by hot objects. At higher temperatures, there is sufficient infrared radiation that we can feel the heat if we are close to the object. At still higher temperatures, on the order of 1000 Kelvin or 727 degrees C. Now the Kelvin scale, of course, degrees Kelvin is equal to the degrees C plus 273. So the scale is developed from the absolute value scale, or from the idea that, or from the concept that absolute value is at negative 273, which would leave a Kelvin value of 0. So Kelvin degrees temperature, the smallest you can have is 0, which would indicate minus 273, which is the coldest anything can actually be. So objects actually glow, such as a red-hot electric stove burner. Now, before we go on, we should like to take a look at this. So first of all, if we increase wavelength in one direction, so increased wavelength, we have infrared, which is higher than ultraviolet. And of course, in between here is the visual spectrum. So remember Roy G. Biv? So the R part is on the infrared section and the violet is on the ultraviolet section. So this little region in here that we can actually see is Roy G. Biv, or red, orange, yellow, green, blue, indigo, violet. So of course, if we get increased the temperature, the colors that we see get shifted to the left. So increased wavelength is corresponded by a decrease in frequency, so they're inversely related. So if I go this way, it's increased frequency, decreased wavelength. If I go to the right, it's increased wavelength, decreased frequency. So if something is hot, we kind of view hot things as being red, right? So the red-hot electric stove burner is red, and we would view it like that. At temperatures above 2000 K, or 1727 degrees C, objects begin to glow with a yellow or white color. So it'll be moving into this area. Kind of in the yellow is in the middle of the region. But all these colors combine together to give a whitish color. So white light is a combination of all of these together. So it would be kind of a white color, which would be an indication of all of those visible colors combined together. The light emitted contains a continuous range of wavelengths or frequencies, and the spectrum is a plot of intensity versus wavelength or frequency. As the temperature, now intensity, or how the brightness increases as well as we increase temperature. So a low red, and then as we go this way, increased temperature, things get shifted to the left. The peak wavelengths here, you could think of almost being an average. As the temperature increases, the electromagnetic radiation emitted by an object not only increases in intensity or brightness, but has its peak wave intensity at higher and higher frequencies. So higher frequencies or lower wavelengths. The spectrum of light emitted by a hot, dense body, as shown in the figure on the right or over here, is an idealized black body. Okay, so we can highlight that. A black body is a body that, when cooled, would absorb all radiation falling on it, and so would appear black under reflection when illuminated by other sources. So it absorbs everything. The radiation such an idealized black body would emit, when hot and luminous, would be called black body radiation, though it doesn't necessarily have to be a black in color. Approximates that from many real objects, the 6000 K curve above, in the above figure, corresponds to the temperature of the surface of the sun. So as we get higher frequency, lower wavelength, look what happens. And of course, the intensity of the sun would be in this region here, because it appears kind of yellowish, whitish to us, right? And very bright. We can't even look at it. Whereas we can look at a hot stove element here in the red or infrared region. Okay, so if you increase temperature, your increasing frequency, and of course frequencies and wavelengths correspond to different colors that we see, so things shift this way, going from red to white until eventually the violet region. So it peaks at that part. For lower temperatures, the total intensity drops considerably, and the peak wavelengths occur at longer wavelengths or lower frequencies. So you can see here, when I'm going from something that's 6,000 Kelvin down to 4,500 Kelvin to 3,000 Kelvin, the intensity decreases as well. So this is why objects glow with the red color at around 1,000 K. It's found experimentally that wavelength at the peak spectrum, lambda p, or wavelength at the p or peak, is related to the Kelvin temperature by this little relationship right here. So a constant over here, wavelength, multiplied by the Kelvin temperature. Okay, so we have to make sure it's in Kelvin. And of course, Kelvin temperature is equal to whatever it is in degrees C plus 273. So we can easily find that. And wavelength is measured in meters. Now, what we often find out is that often wavelengths are expressed in nanometers. And 1 meter is equal to 1 times 10 to the 9 nanometers. Okay? And that's, of course, off that purple metric conversion sheet that we have. Okay? So over here, let's look at an example using this idea. A very easy formula. So estimate the temperature of the surface of our sun, given that the sun emits light whose peak intensity occurs at around the 500 nanometer range. So 500 nanometers. So yes, we can see here's a 2,000, 1,000, so 500 would be in this area. And of course, that's kind of like that yellow light area, or of course all those are combined together to give us white light. So let's see if we can figure that out. So first of all, we have to have lambda, or wavelength, in meter sticks. Kelvin temperature is what we're looking for. So we have to convert this into meters. So 500 nanometers, and of course 1 times 10 to the 9 nanometers is 1 meter stick. So that's how we can convert nanometers into meters. And that works out to be 5 times 10 to the minus 7 meter sticks. So we have to ensure that our wavelength is in meters to use this little relationship. So lambda p for peak wavelength multiplied by the Kelvin temperature is equal to 2.90 times 10 to the minus 3. So if we substitute this in, this is what our lambda is. And this is, now notice here, this unit here is meters multiplied by K. I could show that, I suppose I should write that in meters Kelvin. Over here we have Kelvin multiplied by temp. 2.9 times 10 to the minus 3 meters Kelvin. And of course, to get T by itself, divide by 5 times 10 to the minus 7 Kelvin, divided by 5 times 10 to the minus 7 Kelvin. Notice what happens here, the Kelvin cancels, and I will end up with, I did mix that up. Wavelength is in meter sticks, of course. Yes. Sorry, folks. So meters. I was wondering why I was canceling the wrong thing. So with that, meters and meters cancel, and I'll be left with temperature in Kelvin, which is what I want. So that works out to be 5,800 Kelvin. And if I look at this, if there's 1 sig fig there, of course this rounds off to be 6,000 Kelvin. And of course, back on the flip side, if I look at that page, 6,000 Kelvin. Oh, look at that. There it is right there. So the temperature of that peak wavelength for the sun occurs at 6,000 Kelvin. There we go. Let's look at another example. Suppose a star has a surface temperature of 32,500 Kelvin. What's the color of that star? So of course, color, we can get that by, of course, finding that peak wavelength. And of course, the peak wavelength just represents the average amount here, where it maximizes, where we're likely to see the color. All right? So with this one, we can go on the next page there, because I left some room on the next page to look at this question. So we just flip the page over, here it is. And I also have a electromagnetic spectrum scale over here, wavelength in meters. So it kind of takes this little region right here, this little region of visible light, and expands it out. So we can see that Roy G. Biv, etc. And we can take a look at the corresponding wavelengths. So if we write down a relationship, now we were given, this time it was 32,500 Kelvin. Okay, so we have that. So we have our T, it's 32,500 Kelvin. And of course we're looking for lambda P. And of course that'll be in meters. So we'll have to change back to nanometers to use this. So lambda P multiplied by T equals 2.90 times 10 to the minus 3. So we're looking for lambda, 32,500 K. And of course, yes, I forgot to put in the units for this, which is just simply meters Kelvin. So there we go. And of course here, rearrange and solve for lambda P. Kelvin cancels. That whole thing will cancel, so we'll end up with lambda P is equal to 2.90 times 10 to the minus 3 meters divided by 32,500. And of course, when we solve that, we'll get 8.92 times 10 to the minus 8 meter sticks. Okay, and to use that scale up here, we have to convert it back into nanometers. So 1 meter is 1 times 10 to the 9 nanometers. So of course meters cancel, and we will be left with 89.2 nanometers. Now if I look up over here, let's see, 700, 600, 500, 400, so it'll be way over there in the violet spectrum. Chances are it'll be in the ultraviolet spectrum. So we would say that UV spectrum is where the peak will be. So it'll be kind of like a bluish white type of region. All right, so I'm going to stop the video there. There's a video I'm going to show you that involves someone by the name of Physics Girl, who has a great YouTube channel. It kind of looks at the transition between this idea of the black body spectrum and looks at the ultraviolet catastrophe. Because it looks like if we go with a lower, even lower wavelength or higher frequency yet, this would fall off the chart and be higher than the sun even. But we'll see something that happens in that next video. All right, we'll see you again.